Okay, Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back. It is time for quiz 2. So therefore we have another review. Okay, and very quickly I just wanted to say that this quiz is going to include vector components. So that's the x and y components of vectors as well as trigonometric functions. It's going to include distance and time graphs, so that's as well as position time graphs, speed and time graphs, as well as velocity versus time graphs as well. Okay, so without further ado, I'd like you to please get your calculator and pause the video, try and work out the problem before I work it out. And obviously if if something you don't understand, you can always go back through the video and go through your notes as well. So let's go. Okay. So here we have a question that says a plane flies 300 meters at an angle of 25 degrees above the horizontal. Find the horizontal displacement and find the vertical displacement, which is basically just the x and y components. So what I'm going to do is, first of all, I'm going to show off that, look, I have different colors. Okay, I hope this is clear for you, Mr. Adam Dakur, my student. Hope all is clear. Right, let's have a look. What I need to do is I need to look at what's going on. So the plane's flying 300 meters at an angle of 25. So the best thing to do is to sketch it out. So this is the situation we're looking at. So there's a triangle, there is the angle, 25 degrees, and that is 300 meters. Okay, 300, oopsie daisy, 300 meters. And what I need to do is I need to find the y component and the x component. So that's the vertical component. The y is the vertical. Whoops. Let me just get rid of that. Oh, I'm so over this. Whoops. That's the vertical component. And that's the horizontal component. Okay, so let's have a look. How do we work out the vertical components? Let's switch colors. So that's just going to be SOHCAHTOA, isn't it? So if you're familiar with that, then you're 90% of the way there. Okay, so this is just using SOHCAHTOA. What we need is the sine of the angle. Sine of theta is going to equal opposite over hypotenuse. We've got cosine of theta equals adjacent over hypotenuse, and then we've got tan of theta is equivalent to opposite over adjacent. So if I'm looking for this part here, that is the opposite, okay? That is opposite the angle, so that's O. So, and I've got the hypotenuse, that's the H, the hypotenuse, so I'm going to use sine for this. So sine 25 is equivalent to opposite over 300. And if I want the opposite, all I have to do is sine 25 multiplied by 300, and that should give me the opposite. So the answer is going to be, where's my trusty calculator? Here we go. Sine 25 multiplied by 300, and the answer is going to be 126 meters. 126.8 meters. Don't worry about like how many decimal places. If the question doesn't actually say how many decimal places, then just give an accurate answer. So you can go to 3 significant figures like the question says here, or you can just do 1 decimal place as well, but you gotta make sure the rounding is correct. Okay, so it's 126.785, which is 126.8 to 1 decimal place. What about the horizontal component? I'm going to use green for that. If I do have green, do I have green? Yes, I do have green. Here we go. So what I'm going to do for that one is I'm going to use cosine. And I'm going to go cosine 25 is equivalent to the adjacent, since it's the adjacent side, over 300. And that's going to equal cosine 25 multiplied by 300, 272 meters. Or, since I'm sticking to the same thing I've done before, it's going to be 271.9 meters. Okay? And that's how you do that. So that's both the horizontal and the vertical components. Of course, when I'm labeling this, I'll do that's, oops, sorry, that's A. No, no, no. Oh, no. Can I go back? No, I can't. That's the horizontal, so that's A, and that's B. I hope you can read all of that. Moving on. Explain the motion of the following graphs. So all of these graphs represent motion. But the first thing I need to do when I'm looking at graphs, okay, the very first thing you need to do is make sure you understand what the axis, what the y-axis says, and what the x-axis says. So the labels are very important. Is it a distance time graph? Is it a position time graph? Is it a speed time graph, or is it a velocity time graph? Now, distance time and position time are essentially the same, since we're dealing with motion in a direct line. And for speed time and velocity time, they are essentially the same as well for what we do in this course. So these are both, all of them are distance time graphs. So that means immediately we should know that the gradient or the slope of the line represents speed. Okay, so if it's a distance time graph, the gradient represents speed. So if I look at this one here, that's distance and that's time. What is that telling me? What that's telling me is, let's say for example, that distance is 5 meters. Let's give it a number. 5 meters. And what's happening at 1 second? The object was at 5 meters. What about at 2 seconds? It's still at 5 meters. At 3 seconds, it's also at 5 meters. At 4 seconds, you can see that it's just going to stay at 5 meters. That means the object is stationary. Stationary means it's not moving. Stationary, or you can say stationary, not moving, stopped, at rest. Okay, those are all correct. So if you say stationary, if you say at rest, if you say not moving, okay, or just stopped at 5 meters, that's fine. And if it doesn't have a distance on that side, if it doesn't actually have an actual distance, you can just say the object is not moving at a certain distance. So that's that one. What about that one here? What about this one here? Now we can see the object started at a certain distance, so it didn't start at 0, it started at a certain distance. And then there was an increase, okay, so it kept going up. So as time went past, so here we are, that's 1 second, and it was at a certain distance here. And then at 2 seconds, it is now here, and so on and so forth. So you can see that it actually increases. The distance increases with time. So what do we call that? Do we call that constant increase, that constant, sorry, not a constant increase, constant velocity. Okay, now we just need to figure out, is it positive or is it negative? Is the increase going upwards or downwards? Now we can see that it actually increases positively. So if we say that's 1 meter, that's 2 meters, and so on. So it's increasing positively. So the three ways I would describe this is as such. First of all, it is constant speed, and I should say speed instead of velocity because that's distance, not displacement, because velocity has to do with displacement over time, but speed has to do with distance over time. So since this is distance and time, it is speed. So constant speed, and it's positive since it's going upwards, so I can just say that's positive. And what else do I need to say about this? It's offset, so it starts at a certain distance, it's constant, it's positive. That's probably all I need to say. What about this one here? You can tell just by looking at these two, that's the opposite. That's going downhill. So that's also constant speed. It's the same, it's constant speed because it's a straight line. If it's a straight line, it's constant speed. How do I know? Well, the gradient doesn't change. Remember, the gradient of the line, the slope of the line, represents speed. So if the gradient doesn't change, then the speed doesn't change. So look here, the speed is this here. Oops, that's okay. I should change the color. Let's go with red. That is the speed. And if you look here, that's the speed. And if you look here, that's the speed. It hasn't changed. It's not going like that or whatever. The speed is a straight line. so therefore it hasn't changed. It's the same gradient, therefore it's constant speed. Back to green, constant speed, and this time though it's negative. Okay, let's keep going. What about D? Well, D starts off over here, so it also is offset, so it doesn't start off at 0. But then what happens? Watch what happens. I'm going to go with blue. I've got a gradient over here. I've got a gradient for a line over here. And then over here, it's much, much sharper. Okay, much sharper. So what does that mean? That means the speed has gotten more. Because remember what we said. If it's like that, that's kind of slow. If it's like that, it's faster. And then if it's like that, it's really fast. So therefore, that's gotten faster, hasn't it? Look at the gradient. Look at the difference between the orange and the blue. So that's gotten faster. What do we call that? We call that speeding up. Okay, so that's positive because it's speeding up. And we don't actually have to say positive because it's speeding up. So we just say speeding up or accelerating. And it's non-uniform. Non-uniform means it's not like this. That's uniform. Constant is also known as uniform. Okay, which means it's all the same. And that's also uniform. Okay, what about this then? Oops, sorry. What about this? That's non-uniform. Non-uniform. Okay, so that's the first thing. How is it non-uniform? A straight line is uniform. This line is non-uniform. This line is non-uniform. Okay, that means it's not the same all through. You can see it's not the same all through. Here it was like that, and here it's like this. So therefore, it's not uniform. Now, we need to figure out, is it speeding up or slowing down? Well, you can see the gradient is sharper here. It's much steeper. So therefore, it is speeding up. Speeding up. Or if you want to say positive acceleration, that's fine as well. Over here, it's kind of similar to that one. So it's also non-uniform. And in this instance, it is slowing down. Slowing down. So what's another word for slowing down? We can say decelerating. Whereas over here, we say accelerating. And at this point, I will say that deceleration is part of acceleration, but we will understand if you just say acceleration, it means speeding up. That's fine as well. Whereas here, to distinguish between the two, that is deceleration. What about over here? What's that one? Well, that one is actually very similar to that. Okay, it's very similar to this one here. It's a straight line, so therefore it's uniform, it's constant. Let's go with blue. It is uniform, constant. That's what uniform means. So if you say uniform, uniform speed, that's fine. If you say constant speed, that's fine. And so that's all it is. Uniform, constant speed. Okay, and it's positive. That means it's going up as opposed to going down. It is going forward as opposed to going backwards. If you use forward instead of positive, that's fine as well. If you use backwards instead of negative, that's also fine. Let's keep going. Okay, so here's a live example. We've got distance on the y-axis and time on the x-axis. Remember, that's the first thing you look for. What kind of graph is it? So this is distance time. So that means the gradient represents speed. Okay, so immediately you should know that slope equals speed. Okay, and so how long does the student spend reading the book? So we've got a scenario here where a student goes to the park. They go to the park, they sit down to read a book, and then they run home. And what we are asked to do is answer these questions. How long does the student spend reading the book? Okay, how long do they spend reading the book? So that means that's when they're sitting down. Which section of the graph represents the student running home? And what is the total distance traveled by the student? Okay, fantastic. Really good question. So the first thing is, how long does the student spend reading the book? Well, that's the part when they are not running or not walking and not moving. So which part of the graph represents when they are not moving? Obviously, that's when they're stationary, when they are resting, when they have stopped, and that is over here. That's when the distance isn't changing. Okay, so that's part B. Which section of the graph represents the student running home? When do they go home? Well, that's when they left home to go to the park. That's when they sat down, and that's when they went home. Again, that's when they ran home again. So that's part C. That's when they ran home. And what is the total distance covered by the student? Well, since it's a distance time graph, that's very easy. All I have to do is look at the distance. And the distance covered is 0.6 meters. It's right here. It's right here. So it tells me it's on the graph. It's right here. It's 0.6, not meters, sorry, kilometers. Make sure you look at the units. Okay? Very good. And how long did they spend? Oh, sorry. How long did the students spend reading the book? So it wasn't asking about the section. It's very important that you don't make the same mistake I just made. Read the question carefully. How long did they spend? It's from... Oops. Please stop. Okay, 25 minutes all the way to 65 minutes. So that's 40 minutes. Part B, 40 minutes. Okay, moving on. What does the slope of a distance versus time graph indicate about the object's motion? Well, hopefully by now you should know the slope of a distance time graph represents speed. Let me see if I can write that with my normal handwriting. Speed. Okay. Okay, because it's distance versus time. What does the slope of a speed time graph indicate about the object's motion? So that is going to be something else. That's going to be acceleration. Okay? That's the difference between the two. Okay, let's look at this question now. Which of the velocity time graphs A to E represents the motion of, best represents the motion of a car coming to a complete stop? Okay, so this time we've got a different scenario. We've got velocity time graphs. You see, that's velocity, okay? Not distance, not position. So the gradient represents acceleration or change in velocity. So let's have a look. A car coming to a stop after a traffic light. So in this case, we have to look for the car that comes to 0, where the velocity changes to 0. So where does the velocity change to 0? That velocity is constant. That velocity is not changing. This one here does come down to 0, so that's the one. It's B. All right, so a car coming to a stop at a traffic light, that's going to be B, because the velocity comes down to 0. Now let's look at the next one. A swimmer moving at constant speed. Well, we've just answered that one actually. Constant speed, that means the speed is not changing with time. So as time goes by, the speed is not changing. So which one is it? That one the speed changes, that one the speed changes, that one the speed changes, and so does that one. You can see there's a certain speed here, and then over here it's a different speed. Over here is the same. There's a certain speed here, and then it changes with time. So each one of those shows the speed changing, except for the first one, A. Okay, a cyclist accelerating from rest with constant acceleration. So the word constant is a key word here. Constant means it's not changing. So there is acceleration, so the velocity is changing. However, the acceleration is not changing. So the velocity is changing, but the acceleration is not changing. So what does that mean? That means the velocity could be going up or down, but the acceleration, there's no acceleration. So it's not a curve, right? So it's a straight line. So what are we looking at? Rest with constant acceleration. So accelerating here refers to speeding up or positive acceleration. So that's going to be C. Okay. Next, a car accelerating from rest and changing through its gears. Now that is a tricky one. And really this part here is just there to confuse you. So if we just ignore this part, let's say a car accelerating from rest. Well, that's a very interesting scenario because let's have a look. Cars, when they accelerate, they have a speedometer, right? And the speedometer goes from 0 all the way to, well, it depends on the car, but let's say 240 kilometers per hour. Now, once it reaches that speed, you can't speed up anymore. So the car has a speed limit. Okay, there is an upper limit at which it gets to, and then it can't get faster. So which one is it? It's going to be, well, obviously, since it's accelerating, and it's going to be either D or E, because it's not constant acceleration, it's going to be variable acceleration, right? So non-uniform acceleration. So now we just need to figure out which one of them is it. Well, if we look at E, E is just showing us that the speed keeps going up and up and up and up and up, which means we'll get to a point when the speed is infinite, which obviously isn't true. What's happening in D, however, is that as time goes by, the acceleration slows down, and we get to a point where the speed just tapers off and stays there. It becomes constant. So that is more correct. So it's actually going to be D for that one. That last one is going to be D. Okay. Describe in words the motion of the car. Okay, so here we have another question that talks about the motion of a radio-controlled toy car, and we have to explain what is happening. So let's have a look. That is a position time graph. So that means position time graph. The first thing I need to do is figure out position time graph. That means the slope represents velocity. Okay, so that's position time. Let's see what's happening. The position is increasing. That means there's a velocity, but it's a straight line, so that is positive. Okay, so the first thing that's happening is over here we've got constant or uniform positive velocity. Okay, because it is increasing, so it's positive, and it's constant. The gradient is the same. It's not changing. The slope is the same. And it's velocity, because we know that in a position time graph or a displacement time graph, the gradient represents velocity. What's happening in the second portion here? Well, it went to position 8, and then it stayed there. It went to position 8, and it stayed there for about 2 seconds. So this here is, in fact, let's use orange for that one. This here is showing stationary for 2 seconds. So that means it's not moving for 2 seconds, or stopped for 2 seconds. And then the last part, I'm going to use green. This part here, what is happening with this part is we've got constant velocity as well, but this time it's negative. This time it's going backwards. So it is negative uniform velocity, and I'm going to use uniform this time because I want you to get used to both. Negative uniform velocity. Whoops. And what happens here at this point is we go past the starting point and we go all the way back, and then we stop again at -2. We stop again here. So that is, once again, red. That is going to be stopped. So I could have used stationary, but I just want you to get used to the different terminology. So what happened, we've got a person who started, the car, sorry, let me draw the car. So we've got a car. Not bad. Here we go, that's the car. And we start at position 0. There it is. And what did the car do? It went all the way forward to position 8. Whoops. And then what happened? 8 meters. I don't know why it keeps doing that. So that's 0 meters. And that's 8 meters. And then what happened? It stopped there stopped for 2 seconds. Stopped for 2 seconds. That's what the stop sign looks like. Stopped for 2 seconds. And then what did it do? And then it went back all the way here to -2 meters. And then it stopped for 1 second. Okay, So that's the initial part, 1, and then that's 2, and then that's 3, it went that way, and then 4 is this part here. Okay, 1, it went forwards, then it stopped for 2 seconds, then it went backwards, and it stopped for 1 second. Okay, what was the position of the car after 2 seconds? Well, after 2 seconds, it was at 8 meters. There you go, 8 meters. And if you want to be more specific, you can say positive 8 meters. What about after 4 seconds? 4 seconds, it was... 4 seconds, it was also at 8 meters. It was still there. So, positive 8 meters. What about at 6 seconds? Well, now it's different. 6 seconds, look at that. That was at 4 meters. There you go. Look, 6 seconds. That was at 4 meters. So it was at 4 meters there. No, don't do that. Don't be silly. Here we go. That was at 4 meters. And what about 10 seconds? 10 seconds, it was at negative 2 meters. Look, negative 2 meters. Okay. At what time did the car return to its starting point? So the starting point is this one here, right? The starting point is this one here. Watch the happy car. What is it? Orange. Where's my orange? Here. That's the starting point. Okay, that here, this here is the starting point. So when did it get back to this point, 0? On the way back, it went back at this point here, right here when it got back to 0. So it's 8 seconds, right? So at 8 seconds, at... Stop being silly. At... I gotta figure this out. Sorry about that. At 8 seconds. There. I'm getting angry now. What was the velocity of the car during the first 2 seconds? Okay, so this is important. You need to know that in a position time graph, the gradient or the slope represents velocity. So the first 2 seconds, we're looking at this guy here. Green. We're looking at this guy right here. We're looking at this slope. Okay? Whoops. That one. And so if I'm to calculate the first this one here, the slope, the first 2 seconds, all I have to do is look at the rise versus the run. Okay, now this is important that you know that, okay? So this is the rise, and this is the run. This is really hard. Not the maths, but the drawing part. Okay. Oh boy. Was it doing that? Okay, sorry, I can't really do a straight line. Anyway, that's the rise, and that's the run. So it's 8 over 2. 8 over 2 means that's going to be 4 meters per second. So that's going to be plus 4 meters per second. And the way I said plus 4 meters per second, the reason why I said plus is because it's positive, and I want to distinguish between that and that, okay, because that's going to be negative. After 3 seconds, the speed was what? Or the velocity was what? It was 0. Because it stopped, remember? It's over here. So here it's plus 4 meters per second. Here it's 0. I don't have to say 4 meters per second. I don't have to say that. From 4 to 6 seconds, 4 to 6 seconds, so that's over here. 4 to 6 seconds, it's going down. And I can see that the rise is going to be this one here. And the run is this one here. So it's going to be 4 over 2 or negative 2 meters per second. Now why is it negative 2? Because it's going downwards. So it's going to be the final position, obviously, because remember velocity is displacement over time, and then displacement is going to equal final position minus initial position, so xf minus xi. And then time is just time difference. So if you look at xf, the final position here is 4, and the initial position is 8. So obviously that's negative 4. And then time is 2 seconds, so negative 4 over 2 is going to equal negative 2 meters per second. Okay, that's if you're interested in the maths. Okay, so it's negative 2 meters per second. But you don't have to do all of that. You can just go rise over run, which is 4 over 2. And then because it's going downwards, it's negative. So it's negative 2. What is it at 8 seconds? At 8 seconds, it's also the same slope. Don't be tricked. It's not 0. Remember, this is position time. So the slope is what we're interested in to find the speed. So that is here. That is the same as this. And it's the same as this. Okay? All of them are the same. It's still negative 2 meters per second. From 8 seconds to 9 seconds, from 8 to 9, it's still negative 2, guys. It's that one. Come on. It's that one. That is still negative 2 meters per second. So 4 to 6, it was negative 2. At 8 seconds, it was negative 2. That's the instantaneous velocity, by the way. If you're interested to know, at a certain point, we call that instantaneous velocity. Instantaneous velocity. And from 8 to 9, that's also negative 2. During its 10-second motion, what was the car's distance traveled? Okay, what was the distance traveled? Let's have a look. So they want the distance traveled throughout the whole thing. I need to get rid of all of this just to make things clear. Okay, so just a second. I need to get rid of all of this. You know what's a good idea, by the way, when you're watching these videos, is to have like some tea or coffee. I have my coffee right here. That's good. So let's have a look. What is the total distance traveled? Well, I've gone up to 8 first. So remember, that's 8. And then what did I do? I traveled 10 in the way back because it's 8 plus 2. So 8 plus 10, 18 meters. Okay, 8 up, 10 down, 18 meters. What's the total displacement? Ooh, displacement is the change in position. I started at 0 and I went to negative 2. So that's simply it, negative 2 meters. That's the displacement. Okay, I hope that wasn't too hard. Let's move on. Okay, let's describe the motion of the dog during these sections of the graph. We've got different sections of the graph. There's a dog. I assume the dog is running and starts off at a velocity of 1 meters per second. So it didn't start off at 0. The scenario starts with the dog already running or moving. So we've got a dog moving at 1 meters per second. Then what happens? The speed increases, but uniformly. Okay, so that means it is constant acceleration or uniform acceleration. And then what happens here? We also have uniform acceleration, but this time it's going down, so it's uniform deceleration. And then over here it stops completely. So that's when the speed is 0 or the velocity is 0. Okay, so let's have a look. So over here is, first of all, let's write it in. The first part is constant velocity. This part here is constant velocity. Don't do that. Constant velocity. And this part here, I'm going to go with orange. It's constant positive. You don't have to say positive. If you say constant acceleration, that's fine. We'll understand. What about here? Well, that's also constant. And that's also positive. But this time it's not acceleration, it's slowing down. So we call that deceleration. So it's constant positive deceleration. Now some of you might be wondering, how is it positive? Well, it's because it's above the 0. So it is slowing down, but it's going in a forward direction. So it's slowing down, but it's still going forwards. So, well, in this case, the dog is slowing down, but he's still moving forwards. Now at this point, the dog stops completely. Stops completely, stationary, at rest. And then what happens here? Now that's interesting. What happens here is negative acceleration. This is negative acceleration, not this. This is positive deceleration. And there's a difference between positive deceleration and negative acceleration. Positive deceleration means he's still going forwards, but he's slowing down. Negative acceleration means he's going backwards and he's speeding up. Okay, so now we've got negative acceleration, and then over here we've got constant negative velocity. I suppose I should label this as constant positive velocity. Okay, so that's what's happening. First the dog is moving at constant velocity, then they speed up, then they slow down until they get to 0 and stop. Then they start speeding up backwards. They go backwards and speed up. Then they do what? Then they stop. Okay? Right, calculate the displacement of the dog after 2 seconds. Oh, so now we got to think about something else. I'm going to get rid of all of this, okay? I can do this with one button, by the way. Here we go. Calculate the displacement of the dog after 2 seconds. So this is extremely important. In order to calculate the displacement in a velocity time graph, I have to work out the area under the graph. That's simply it, okay? So it's only going to be squares, rectangles, or triangles. So if it's a square or rectangle, it's going to be base times height. If it's a triangle, it's half base times height. Simple as that. So what I need to do is cut up the graph and then work out the area under the graph, and then it's easy. Just that simple, okay? So let's have a look. Calculate the displacement of the dog after 2 seconds. So let's have a look. So that's 2 seconds over here. That's what they want. They want the area under the graph. So that's going to be 2. Remember, it's base times height. So that's 2. And that's 1. 2 times 1. 2 times 1 means 2 meters. And that's it. 2 meters. That's the displacement. Now you might be wondering, why is it meters and how do I work out the units? Now remember, velocity equals displacement over time. So if I put that in a triangle, this is what it looks like. Velocity, displacement, time. So if I want the displacement, all I have to do is multiply velocity by time. So velocity in this case is 1 meters per second, and time is 2 seconds. 2 seconds is the same as 2 over 1. These cancel out, and then the displacement equals 2 meters. So that's why it's 2 meters. Okay? What about the next one? At 7 seconds. Okay, the displacement after 7 seconds. After 7 seconds, I'm going to use orange. There we go. Where's 7? Here we go. So they want, this time they don't just want that, they want the whole thing. What color is this? I thought it was orange. Oh, it's green. Okay, here we go. So what do? Well, I need to do something, and what that something is going to be is I'm going to cut it up. So I'm going to go with red, and I'm going to cut this up. So I'm going to go put a line down here, and I'm going to put a line here. Now you don't have to cut it the way I did it. You don't have to cut it the way I did it. You can do it your own way. It doesn't matter. It'll give you the same exact result. And I'm going to work out the area of these. So the first one I'm going to start with is this rectangle over here. That's going to be 1 by 1 multiplied by 4, right? 1 multiplied by 4. So 1 times 4 equals 4 meters. Okay? Now I need to figure out the rest. This one here is 2. How is it 2? It's between 2 and 4. 4 minus 2, so that's 2. And then this one is 3 minus 1. Don't go 3. Don't make this mistake. It's not 3. It's 3 minus 1. It's the difference. 3. See, this is 1 here, and that's 3. So we want 3 minus 1, so that's going to be 2 as well. It's not to scale, obviously, so it's going to be 2 times 2, which is 4, but then you got to cut it in half because it's a triangle. Okay, so it's half base times height. So it's half base times height, area of a triangle, area of triangle. area of triangle equals half base times height. So which is going to be half times 2 times 2, which is equivalent to 2 meters, because it's 2 times 2, which is 4, and that's 2 meters. What about this one here? Okay, think about it. It's going to be, sorry, I just need to write the answer here. And then the third one, I'm definitely going to use orange this time. The third one, what's it going to be this time? Well, I've got a height of 3. Now this time it is the full 3, because it's 3 minus 0. See, it's 0. And then it's 3 here, so it is the full height. So it's 3 minus 0, so it's 3. That's the height. The height is 3. And what about the base? The base is also 3. See, 4 to 7. 7 minus 4, it's 3. So 3 times 3 is 9, but then you've got to cut it in half. Don't forget to cut it in half. So that's going to be 4.5. Okay? 4.5. And so the total displacement is going to be 4 plus 6. 4 plus 2, sorry, which is 6, plus 4.5, which is 10.5 meters. At 7 seconds. Whoops. Why did I do that? So that's only the second part. What about at 10 seconds? Okay. Now let's have a look. At 10 seconds, I gotta add this part here. Ooh, but now this is interesting. Let's go green. So it's gone forwards. It's gone forwards by 10.5. But then it's gone backwards, and we got to figure out what this area is. So once again, it's the same exact thing, guys, same exact thing. So here it's 1 times -1, so this time it's -1 meters. Okay, don't forget the negatives. That's -1 meters. And then what about this portion here? Oh, I've got to do better than that. Hang on. I'm gonna cut this up into a triangle. Oh, this is taking every single skill. Oh man. Okay. Try again. Don't give up. Don't give up. All the boys are watching. Not yet. There's no good luck yet. Here we go. That's better. That'll do. Okay. 1 times 1, so that's -1. That's not -1. That's 1 times -1 divided by 2, which is -1/2. I'm sorry, I'm distracted by all the technical problems I'm having today. So excuse my little tiny mistakes. Okay. Okay, so let's just say that's -1/2. I know it's not working, but that's -1/2. Yay, and -1. So the total here is -1.5. And over here, it's positive 10.5. So the total displacement is going to be positive 10.5 minus 1.5, which is equivalent to 9 meters. And it's still positive 9 meters. I'm so frustrated by all the technical issues. Anyway, guys, thank you so much for paying attention today. I hope you find the quiz easy. Just make sure you understand the concepts we've talked about today. And if you have any questions, ask your friends. And if you really still don't understand anything, ask me. Now, good luck. Take care. Bye-bye.